Good afternoon, everybody. I'm George Styan, and I'm going to introduce two videos which were made specially for the recent meeting, International Workshop and Conference on Combinatorial Matrix Theory and Generalized Inverses for Matrices at Manipal University in Manipal near Udupi, Karnataka, India, from the 2nd to the 11th of January 2012. The first video is entitled An Introduction to Yantra Magic Squares and Agrippa-type Magic Matrices, and it was presented on Thursday, the 5th of January 2012. We're here in the Ammerlaan restaurant in Stanley Street in Montreal on Friday, February the 17th, 2012, and I'm very grateful to Thomas Ammerlaan for once again borrowing all of the video equipment, and to Karl Chu, who is helping with his own video equipment in making this video. The talk is actually based on joint research with Karl Chu and Gert Frankler, and is presented in considerable detail in a set of lecture notes which are from the Department of Mathematics and Statistics at McGill University, and which will become available also in Manipal University. The invited lecture was actually presented as a video on Thursday the 5th of January 2012 in Manipal, and my thanks go especially to Christian Boyer for constructing the 22 by 22 Fermat-Boyer Magic Square, and to Daniel Rosenthal for drawing the Jupiter planet Yantra. And I might mention that a silver Yantra was seen by us yesterday in the Colors of India exhibit at the Pointe à Callière Museum in the old Montreal part of the city of Montreal, where we visited yesterday. I recommend this exhibit to everybody. In addition to Thomas Ammerlaan and Karl Chu, who we already mentioned, I also am grateful to Nicolas Ammerlaan, Oscar Maria Baxellari, Sam Drury, and Evelyn Styan for their help. The research was supported in part by the Natural Sciences and Engineering Research Council of Canada. The handwritten image of the 14 by 14 Fermat Magic Square by Félix Victor-Zia is from manuscript number 10556 in the Département de Manuscrits, Bibliothèque Nationale de France, Paris. My sincere thanks go to Christian Boyer for the image of this square, and to the Bibliothèque Nationale de France for allowing us to reproduce it here. Hello everybody. I want to tell you today about Yantra magic squares and Agrippa-type magic matrices. And I want to tell you how the magic matrices that were first considered, as far as I know, by Agrippa, Cardano, Paracelsus, and Kircher may be constructed. I'll, from time to time, illustrate my findings with postage stamps. As many of you probably know, magic squares are figures resembling a chessboard in which the terms of an arithmetical progression are so arranged that their sum, whether taken diagonally or by rows or columns, is always the same. The construction of such magic squares, containing an odd or even number of cells, had been known to the Hindus for a long time. In Tantra Sastra, they are called Yantras. So wrote Padmakara Dwivedi in his introduction to the Ganita Kaumudi by Narayana Pandita, published in 1356. A 9 by 9 composite Navagraha Yantra magic square is shown in this overhead, where we have placed in a 3 by 3 arrangement several 3 by 3 magic squares to form a composite magic square. In this talk, we will study various properties of Yantra magic squares. Yantra is a geometrical diagram used like an icon, usually in meditation. Indeed, magic squares were first considered as part of occult philosophy, later became part of recreational mathematics, like the Sudoku puzzle, and more recently have been considered as a topic in research mathematics, particularly in matrix theory and combinatorics, the two key subjects of this workshop and conference. A classic n by n magic square or magic matrix is an arrangement of the numbers 1, 2 up to n squared in an n by n array so that the numbers in every row, every column, and in the two main diagonals add up to the same magic sum. M equal to n into n squared plus 1 over 2. When n is equal to 3, the 3 by 3 classic Luoshu magic matrix is 492, 357, 816 with M magic sum equal to 15. We begin with 3 by 3 magic squares depicted on planet Yantras. For these 9 planets, the sun or Surya, after which Sunday is named, the moon or Chandra, after which Monday is named, Mars, Mangala, after which Tuesday or Mardi is named, Mercury, Buddha, or Mercredi for Wednesday, Jupiter, Brihaspati Guru for Jeudi or Thursday, Venus, Shukra for Vendredi or Friday, Saturn, Shani for Saturday, and then these two extra, not really planets, Rahu and Ketu. The lunar nodes Rahu and Ketu are the points where the moon's path in the sky crosses the sun's path, as you can see in this diagram. We will also consider Navagraha Yantras, 3 by 3 arrangements of the 9 planet Yantras, usually with a sun or Surya planet Yantra in the center. Here are examples with the characters in Sanskrit or the more usual characters that we're used to. The sun, planet Yantra, is in the center. We can construct 8 of these, as I will show you in a bit. I want to illustrate these things with postage stamps, and here is an illustration using postage stamps. It's a 3 by 3 arrangement. You'll see the stamp from Jaipur, which used to issue its own stamps, in the upper row center. In the upper right, you'll find Rahu on a stamp from Laos. On the upper left from Dahomey, one of Venus. Saturn, Jupiter, and Mars are in the center row. In this particular arrangement, Jupiter is in the center as opposed to the sun in the early ones. Bottom left is Moon, moonlight. In the bottom center, that's not a stamp. I couldn't find a stamp for Ketu. And in the bottom right is Mercury. The matrix, as you can see, is 618, 753, 294. Jupiter in the center. The stamps in the central row come from Ciskei, which is now part of the Republic of South Africa. Upper left, Dahomey in Northwest Africa. Jaipur in India. Laos in Southeast Asia. Italy and Austria in Europe. The only images of the 9 planet yantras depicting magic squares that we have found each depict a 3 by 3 magic square, respectively L1, L2 up to L9 as defined there. And L1, you will notice, is a double flipped version of the standard Luoshu matrix there in the middle, 492, 357, 816. F is the 3 by 3 flip matrix, and we will be doing quite a bit of flipping in the rest of this talk, so that's a matrix to keep in mind. F for the flip matrix. L0 for the standard Luoshu magic matrix. Most of the planet yantras with 3 by 3 magic squares that we have found show the numerals in Sanskrit, with the number 9 depicted in 2 different ways. I do not know why that has come about. The directory that I have found for the Sanskrit numerals is given in the bottom right panel, and in the central panel you'll see that symbol that looks like a euro sign or the British pound sterling sign, used also for what might be considered a backwards 9 as the Sanskrit symbol for 9. Here are some Navagraha planet Yantras arranged as 9 by 9 composite magic squares. Again, now we have Jupiter in the center. In the right panel, the Sun is in the center left. In the left panel, the Sun is in the center top. Our Navagraha 9-planet Yantra magic square is defined by the 8 composite 9 by 9 fully magic matrices. Here the cross on the circle means the Karnataka product. So this yields 8 classic 3 by 3 magic matrices. The top left with the top row 618, the top center puts the 618 on the bottom. The top right has the 618 flipped. The central arrangement 672 as the first row, that's the first column from the upper left, and so on. You can see the usage of the flipped matrix and also the transposition of L1, which we indicate by L1 prime. The magic square defined by M7, 492357816, which we also coded as L0, the classic Luoshu matrix, was chosen as the table of Saturn and his compass by Heinrich Cornelius Agrippa von Nettesheim, 1486 to 1535. His publication was just before he died. I understand the first time was publication in 1531. Girolamo Cardano, living slightly later, named the same magic square Luna after the moon rather than Saturn. In the magic square M7, as we've already noted, the numbers in the rows, columns, and 2 main diagonals all add up to the same magic sum, 15. Another scholar of that time period was Paracelsus, born Philippus Aureolus Theophrastus Bombatus von Hohenheim, a Swiss scholar. Agrippa was German, Cardano was Italian. He named the magic square defined by M2, the talisman de Saturne, or Samedi, meaning Saturday, the planet Saturn. And here are the 9 by 9 composite magic matrices, where each matrix element of these matrices is a 3 by 3 submatrix. As you can see, L5 sits in the center, and then are the 8 possible variations. For example, N1, the first of those, if you write it out completely, looks like this. The n by n magic matrix M with magic sum little m is said to be F associated whenever m plus fmf is 2 times the magic sum times the matrix with every element equal to 1 over n. So m plus fmf, every element is equal to 2 little m over little m. And f is, as before, the flip matrix, the reverse identity matrix with 1s on the backwards diagonal. If m is equal to n into n squared plus 1 over 2, then 2m is n into n squared plus 1, and you divide it by n, you get n squared plus 1. The magic matrices n1 up to n8 all have magic sum 81 and rank 5, and all are F associated, since the Kronecker product F3 with F3 gives you F9. In an n by n F associated magic square with magic sum little m, the sum of pairs of entries diametrically equidistant from the center are all equal to 2m over n. An F associated magic square is often called just associated, with no qualifier to the word associated, or regular or symmetrical, and these have been widely studied. Magic square planetary talismans, or MSPTs, were created from 1531, as I mentioned before, up to 1653, as I will now mention, by Athanasius Kircher, who was also German, like Agrippa. We already talked about Cardano and Paracelsus, respectively, from Italy and Switzerland. The 7 planets that they were interested in were Saturn, Jupiter, Mars, the Sun, Venus, Mercury, and the Moon. We found postage stamps for 3 of these 4 scholars. Agrippa seems to have eluded the philatelic world. Cardano has only very recently appeared on a stamp, and this is an external airmail stamp from part of what is now Russia, the Russian Federation, called Altai. Paracelsus has appeared on many stamps, particularly those from Switzerland, his home country, and Anastasius Kircher has appeared on only 1 stamp, curiously from Malta. As mentioned earlier, Kircher is from Germany. Agrippa was a German magician, occult writer, theologian, astrologer, and alchemist. His magic square planetary talismans, or MSPTs, were first published in 1531 in his De Occulta Philosophia Libre 3. Cardano was an Italian Renaissance mathematician, physician, astrologer, and gambler. His MSPTs were first published in 1539 in his Practica Arithmetici et Mensurandi Singularis. As you can tell, both of these are in Latin, and when I studied Latin I was a lot younger than I am now. Paracelsus was a Swiss Renaissance physician, botanist, alchemist, astrologer, and general occultist. His MSPTs were first published in 1567 in Archidoxa Magica. Kircher was a German Jesuit scholar who published in the fields of Oriental studies, geology, and medicine. His MSPTs were first published in 1653 in Oedipi Aegyptiaci, Egyptian Works, Tomi Secundi, the 2nd volume. So you can see a diverse collection of pursuits by these 4 scholars, all of whom also looked at and produced magic squares. We'll concentrate on the magic squares of Agrippa and Cardano, and here you see the 3x3 taken from the original works by Agrippa in the left panel and Cardano in the right panel. The left panel by Agrippa was dedicated for Saturn, and the one on the right was dedicated for the Moon. The Agrippa-Cardano magic square, as I've already mentioned, with the 492 on the top row, is the classic Luoshu magic square, or Luo River writing. Legend has it that the very first magic square was discovered in China about 4,000 years ago on the back of a turtle in the river Luo, a tributary of the Yellow River in China. Here are the 2 5x5s. I'm skipping the 4x4s for the moment. I'm concentrating now on the odd order magic squares. Here are the 5x5s. On the left by Agrippa for Mars, on the right by Cardano for Venus. They're the same magic square. And again the 7x7s, the same magic square, on the left by Agrippa for Venus, albeit with a typo, and on the right by Cardano for Mars. The Cardano one appears to be without a typo, and you can see the problem with that 39 in the red circle. The 9x9s that were produced by both Agrippa and Cardano and their original works both had a typo in the top row. The 45 should have been a 54, and the Agrippa one has the additional typo of a 35 that should be like a 38, as Cardano had. By Agrippa for the Moon and Cardano for Saturn. We may generate odd order, Agrippa-type or Agrippa-Cardano or Agrippa-Cardano-Paracelsus Kircher magic matrices using a magic matrix algorithm, which we believe to be new and which we will now describe. Our magic matrix algorithm generates classic non-singular n by n magic matrices A sub n for any odd number n greater than or equal to 3. The MATLAB algorithm, Magic of N, by Cleve Moeller, first announced apparently in 1993, also generates classic non-singular n by n magic matrices with n odd, but they, apparently all for n greater than or equal to 5, essentially differ from our Agrippa-type magic matrices. Our algorithm is based on the one-step forward shift matrix, which is often used in the statistical analysis of time series. You see ones in the n-1 positions on the leading principal superdiagonal and in the bottom left corner, and though is a circulant. When n equal to 5, we have this matrix S5. We now define the n by n matrix T sub n as the difference between Sn, that you just saw, the one step forward shift matrix, and its transpose, which is also its inverse. When n is equal to 5, you see there T5, minus 1s on the principal subdiagonal, and in the top right-hand corner, plus 1s on the upper principal subdiagonal in the lower left corner. We now define the matrix Un, which is a flipped Tn minus n times Tn, and so there are differing formulas for it, as you can see. And for n equal to 5, the flipped matrix F5 has the 1s in the backwards diagonal, and the T5 matrix has a 1 in the top left-hand corner, and then minus 6, minus 5, minus 6, minus 4, minus 5, and so on. The elements are curiously distributed, and it's not at all obvious if you see the matrix T5 that it really is a function of the matrix Sn. We now have 3 equivalent formulas for our magic matrix algorithm. Formula 1 takes the matrix Un from the previous slide and adds 1 over n to every element and then inverts. In Formula 2, we take the matrix Un and add a quantity to every element. That's a bit more complicated, and then invert. And in Formula Right, we take the Moore-Penrose inverse of the singular matrix Un and scale it and add a multiple to, add the same number to every element. The matrix E bar n has every element equal to 1 over n, and Un is this function of the one-step forward shift matrix. So once again, there's S5, and there's U5, and down there is A5 that we get by using U5, adding to it this multiple of the E bar 5 matrix, inverting, multiplying by 120, and we get the matrix that's shown there, the Agrippa-Cardano 5 by 5 that we looked at earlier. Now let's look at the 4 by 4 Agrippa-Cardano matrices. We're now doing the doubly even MSPTs. This was Agrippa's choice for Jupiter, Cardano's choice for Mercury. The 8 by 8 is the only other doubly even one. Agrippa chose it for Mercury and Cardano for Jupiter. Generating Agrippa-type magic matrices with n doubly even has been described in some detail by Kirkland and Neumann in a seminal paper in 1995, and as already mentioned, Moeller generated magic matrices, first publishing news of this algorithm in 1993, and then in a book in 2004. We find that our Agrippa-type magic matrices are simply the MATLAB ones when n is a multiple of 4, that is doubly even, with the rows flipped. So our A4 and A8 are the row flipped M4 and M8 from MATLAB as shown here. Our procedure for generating Agrippa-type magic matrices appears to differ from the algorithm given by MATLAB, and it uses a partner or B matrix or magic basis matrix Bn defined as above. You take the matrix An multiplied by n, then take its transpose and do a double flip and some scaling. You can go back and forth. An is uniquely determined by Bn and vice versa. The Bn for 4 and 8 are shown here, and you can see a remarkable pattern. The 8 by 8 matrix B8 is bordered, really two-bordered. Whenever I mention bordered in this talk, I really mean bordered with 2 rows and 2 columns, in that the 4 by 4 inner core, B4 super 8, say, formed by B8, by removing its top 2 rows, bottom 2 rows, first 2 columns and last 2 columns, is also a magic basis matrix. So you can see that the B4 that's shown in the overhead is in the inner 4 by 4 core. Here you see the Agrippa-Cardano A4 and A8 with in A4, 4 in the top left-hand corner, and A8, 8 in the top left-hand corner. Then as you progress down the main diagonal, you see that the gap size on the left is 3, and the numbers are in arithmetic progression, 4, 7, 10, 13. And on the right, the numbers have gap size 7, that's 1 less than 8, 8, 15, 22, 29, and so on. Both matrices have a 1 in the top right-hand corner, and in the bottom left-hand corner is n squared. In the left it's 16, and on the right it's 64. We call this two diagonals in progression property 2-dip. The parameters are n and 1 for the top left and upper right corners, and n minus 1 and n plus 1 for the 2 gap sizes. As you go down the left-hand, the main forwards diagonal of A4, you see a gap size of 3, which is 4 minus 1. And as you go down the main backwards diagonal, the gap size is 5, or n plus 1. The 8 by 8 magic basis matrix B8 you see here, and you see that the top row contains precisely 4 entries equal to minus 7 and 4 entries equal to plus 7. And the second row contains precisely 4 entries equal to minus 5 and 4 entries equal to plus 5, and so on. We can therefore scale things, but before doing that scaling, we'll just say that the matrices An and Bn I will call smooth whenever in the 2-dip magic basis matrix, as you see here, the numbers in row R add up to 0 and are all equal in absolute value. Minus 2r plus n plus 1 when r is less than or equal to a half n, and 2r minus n minus 1 when r is greater than or equal to a half n plus 1. And we find that A4, A8, B4, and B8 are all smooth. We will say that the n by n matrices An and Bn are row balanced whenever we have this property that I plus f Bn is 0, or that Bn is equal to its row flipped version with a change of sign. We will say that the magic matrices are column balanced when, without a change of sign, flipping the columns gives you the same matrix back again. Bn is equal to Bnf for the magic basis matrix. And we will say that the n by n magic matrices An and Bn are, with doubly even n greater or equal to 4, are doubly balanced whenever they are both row and column balanced. So if you flip the columns, you get the same matrix back again. If you flip the rows, you get the same matrix with a sign change back again. And we find that A4, A8, B4, and B8 are all doubly balanced. This will lead us to a reduced magic basis matrix. From the special sign pattern in each of the rows B8 together with B8 being smooth and doubly balanced, we find the following procedure for generating n by n doubly balanced Agrippa-MATLAB magic basis matrices for doubly even n equal to 4, 8, 12, and so on. Here's the formula for an, and now look at the formula for bn. We have in the middle there a column vector bk, where k is n over 2, and its transpose. The diagonal matrix dk does the scaling, and the big matrices, which are the partition matrices, inflate the little reduced thing in the middle to the full bn. So all we need is the generator b sub k. We have found 3 generators that work. There may very well be others, but we don't know them at this time. An open question and I guess an exercise for the students among you. The first one, which generates the Agrippa-Cardano matrices, takes +1, 2 minuses, 2 pluses, and so on, up to the very end, which is a minus. Drury created an algorithm for generating classic 2-dip smooth, doubly balanced AN with magic basis matrix B super 2. He took pluses for the first n over 4 entries and minuses for the last n over 4 entries. So the sign change is between positions n over 4 and n over 4 plus 1. An algorithm given over 100 years ago by Cavendish used or suggests using, he didn't have the vector bk, but his method leads to a vector bk here super 3, where the signs alternate, plus minus, plus minus, plus minus, and so on. With n equal to 4, the 3 choices all give the same fellow, the Agrippa-Cardano matrix that we saw earlier. The vector b2 is just +1, -1. For n equal to 8, the vector b is 4 components. If we use the original Agrippa-MATLAB version, we get plus, minus, minus, plus. With the Drury version, we get plus, plus, minus, minus. And with the Cavendish version, we get plus, minus, plus, minus. And you can see here these 3 matrices. I was reading an article by Fulkerts just a few hours ago before making this tape, and he suggests that, or observes that the second version there, A8 super 2, is due to Picatrix. Picatrix is a manuscript that is in a museum in Krakow, Poland, and further research on that will be needed. So now we're going to discuss generating Agrippa-type matrices, magic matrices, for singly even. We have only a singly even one to go on, that is of order n equal to 6. The orders were from 3 to 9, and the only singly even number, as I'm sure you all know, between 3 and 9 is 6. The Agrippa-Cardano magic matrix is shown here in the middle, and we're now going to discuss how to generate certain, what I will call Agrippa-type matrices, though they will end up being Agrippa-Fermat magic matrices, because we will use a result of Pierre de Fermat of Fermat's last theorem fame. Our matrices will satisfy certain desiderata, which will appear shortly in table 6.1. We will use a 14 by 14 bordered magic square due to Pierre de Fermat, and so we will call our matrices A6, A10, A14 Agrippa-Fermat magic matrices. We also use a 22 by 22 magic square, specially constructed for us à la Fermat by Christian Boyer in Paris. Christian tells me that the method he used was the same as the method used by Fermat in a letter to Pierre Marin Mersenne, the original copy of which has been lost, but a handwritten copy by Félix Vic d'Azir is in the Bibliothèque Nationale de France in Paris, and we are hoping to get permission from the BNF to include an image of it in the lecture notes. Pierre de Fermat has appeared on several postage stamps, including this one from France, which also shows Fermat's last theorem. On the right is a stamp from Liechtenstein with a Mersenne prime number on it. In table 6.1, you see the desiderata for our Agrippa-Fermat magic matrices A sub n equal to singly even 4k plus 2 greater than or equal to 6. The first desideratum is that they be classic with entries 1, 2 up to n squared in some order, magic sum n over 2 times n squared plus 1. 2 dip with parameters n, 1, n in the top left, 1 in the top right corner. Gap size is n minus 1 on the main forwards diagonal, n plus 1 on the main backwards diagonal. Non-singular and with a partner B bar matrix of full row rank n over 2. The B bar matrix is n over 2 by n and is the scaled version of the B matrix when all the elements have been scaled to plus or minus 1. That is, it has to be smooth, as in point 5. It has to be row balanced because we want Bn after a row flip to be equal to the original Bn with a sign change. We want it to be bordered, as you will see below in figure 6.2, and with characteristic polynomial det lambda I minus Bn equal to lambda to the n minus 3 times lambda cubed plus 120. We find it rather curious that the eigenvalues are the cube roots of minus 120. For n equal to 6, the B bar matrix is in the bottom right hand corner where you see the numbers plus and minus 1. The bigger one with the bottom part being a reflection of the upper part and has the original scaling 531, 135, which we can take out. So we can reduce things to this so-called B bar or reduced magic basis matrix. The magic basis matrix B6 is row balanced in that its last 3 rows flipped coincide with its first 3 rows with a sign change. And we're going to write that as J6,3, meaning the 6 by 3 matrix that you see there with the identity on top of minus the flip matrix. D3, the 3 by 3 diagonal matrix with elements 5, 3, 1. And the B bar matrix, as you see there, 3 by 6. We'll also call this reduced magic basis matrix the B bar matrix. Our reduced magic basis B bar matrices for n equal to 6, 10, 14, 18, 22, and 26 are shown in the picture below. The full 13 by 26 matrix is B bar 13, 26. If we remove the brown border, we get the 11 by 22 matrix B bar 11, 22, and so on, all the way down to the green border. Removing it gives the 3 by 6 B bar 3, 6 for the original Agrippa-Cardano matrix A6. The B-bar matrices B-bar 510 and B-bar 714 are based on the 14 by 14 Fermat magic square. The B-bar matrices B-bar 918 and 1122 are based on the 22 Fermat-Boyer magic square. And here it is, the beautiful 22 Fermat-Boyer magic square constructed by Christian Boyer, specially for us, à la Fermat. The B-bar matrix for the Fermat-Boyer matrix, as you can see now, is not smooth. But, using an expression I learnt from my colleague Sam Drury, we can move the furniture around a bit in this matrix, as you will see by the cells that are in dark blue and purple and red. We move those about and we get a beautiful, smooth B matrix. Come see. With some trial and error, we now can generate a B-bar 13 by 26 magic basis matrix. And then we can construct its partner Agrippa-type magic matrix A26. Our pièce de résistance. I wonder if that has been published before, but I somehow doubt it. And I also wonder how many of these there are. And my guess is there are one hell of a lot. More than 85,248. I'll come back to that number in a minute. I told you that Fermat has appeared on several postage stamps. Germany recently has produced what are called individual stamps. They call them Marke individuell. And there is a maxi card for Pierre de Fermat showing a statue of him in his birthplace of Beaumont de Lomagne. Here are the two 6x6 magic square planetary talismans, or MSPTs, by Agrippa and Cardano, both for the Sun. Here is the matrix, and we believe it to be not the only 6x6 classic non-singular row-balanced smooth two-dip magic matrix. The B-bar 3-6 that generates the Agrippa-Cardano 6x6 is shown here, and I have encircled in red the -1s that are determined by the two-dip property. Then in addition you can see that in the top row the free -1 is in column 3, the second row the free -1 is in column 1, and in the third row the free -1 is in column 2. We may therefore write B-bar 3-6 equal to B-bar 3-6 super 3-1-2. In all, there are 64 equal to 4 cubed possible versions of B-bar 3-6, running from B-bar 3-6-2-1-1 to B-bar 3-6-5-6-6, with just 16 flavor A yielding a classic non-singular fully magic matrix confirming a result of Drury. The 48 singular magic matrices all have rank 5, with 24 having magic basis partner B of rank 3, we call that flavor B, and 24 of rank 2, we call that flavor C. None of these 48 singular magic matrices are classic. In how many ways, call it X, and in which ways can we create a 5x10 reduced magic matrix B-bar 510 that is partner to a classic non-singular two-dip smooth Agrippa-type magic matrix A10 that satisfies our 7 desiderata? The answers seem to be related to the number of ways W1 and in which ways we can set up the plus or minus 1 in the green cells below so that the full 5 by 10 B bar 510 partners a classic smooth non-singular 2-dip 10 by 10 Agrippa-type matrix A10. The plus or minus 1s in the 22 brown cells are fixed. The row sums must all equal 0, and so W1 is 56 squared. Let the 3 by 2 blue matrices be Q1 bottom left and Q2 bottom right. Here you see that Q2 is simply the column flipped Q1. Then we may choose the plus or minus 1 in the blue cells in 2 cubed or 8 ways. Hence x is presumably less than or equal to W1 times W2, which is 25088. This is the problem that I'm currently working on as we are making this video on Wednesday, December the 28th, 2011. Maybe by the time you hear these words, I will have the answer and I will have been able to communicate it to you. But if I don't have the answer, or if you have not heard the answer from me, please do not hesitate to get in touch with me at styan@math.mcgill.ca. Thank you very much.